mathematician, but when I traveled to the field and I conducted field work on the Arctic sea ice, and this is the permafrost area. So we need to because it's useful to understand what you study. Okay, let's discuss the first thing. First thing, the Arctic sea ice. What's going on where? So let's show this one first. So this study Arctic sea ice pack, and ice pack, the thickness few meters of the Arctic ice pack, and on the surface of ice pack during summertime you can observe so-called meltpoints. And compared to the past, when we observed like little number of meltpoints, now we can see a good complex network of meltpoints. If you're looking from helicopter, for example, a nice picture of these meltpoints covering Arctic sea ice in summer. Why it's important? Because it's these guys changing albedo of this Arctic climate system, because meltpoints water can absorb radiation and then transfer into the ocean, and then it can accelerate sea ice albedo feedback. And what we can see from real observation, if it's meltpoint coverage, meltpoints growing from the beginning of June, and it's a rapid process, only 2 weeks, and we get such a nice picture. But the albedo is drastically changing, dropping down. And it looks like a critical behavior in physical system, like some kind of phase transition. Meltpoints are very important, and modeling meltpoints is really important too. And many models like Danny Feltham, University of Reading, for example, is developing many different nice models for meltpoints. But our goal, it was to study meltpoints like a steeping element and see why this transition, phase transition, happening in this system. And because also we want to use mathematics and physics and see how it's the powerful and universal, because besides of this thing that we study climate system, the main goal is our work to see that mathematics can work everywhere. So what actually found? I was a postdoc at the University of Utah and worked with Ken Golden, who is the main guy in mathematics sea ice. And actually, his team analyzed about 5,000 images of the Arctic sea ice surface, taken from a helicopter. And we studied just a simple geometry of the surface of this meltpoint. And we just calculated perimeter and area, what we can usually do if we have this satellite or helicopter images. And we found like these points transferring from a simple circle to a complex network in terms of the geometry. And in mathematics, one of these parameters, what we can use to study geometry, it's called the fractal dimension. Fractals are self-similar objects. And when we zoom in, we can see the same geometry of like at the beginning of our observation. And zoom in, and and we see the geometry of the patterns are similar. But it's not about this, it's about just mathematical parameter what we can use called fractal dimension. The fractal dimension of a simple shape can be simply computed through the perimeter and area. But if you know the side of the simple shape, right, you can just compute area, perimeter, and get the fractal dimension. And the fractal dimension of the simple figure like this, it just like a dot, it just one. And in 2 dimensions, right, the fractal dimension will be 2. But for such objects, fractal dimension is something between 1 and 2, because these objects are wiggling. They are not simple actually. And when for clouds, fractal dimension, it's about 1 32, for example. Sean Lovejoy computed in late 80s the fractal dimension of clouds. So interesting parameter what can allow to us to study geometry of this. And what if we make this revision of perimeter area computation in terms of fractal dimension versus area, we can see this transition and what's happening on 100 meters square. So the complexity is increasing from simple object at 100 meters square. These points actually becoming very complex, complicated object. And it looks like again, like phase transition in physics. By the way, in physics, they know different systems like thin films or magnetic domains, but it's a different scale. The scale is microns. Here, points, they scale meters, but for such domain structure, magnets or thin films, they scale microns. But anyway, patterns formally they remind us these small points. And what we decided to do, we decided to employ the theory what describing formation of magnetic domains in the magnets to study meltpoints. And I'll show what we got, but first, very simple introduction to disordered system and what's going on in such magnetic. So if we have a simple experiment, let's see, we have a magnet, we have a handle and a nickel, like a US dime actually. If you have, you can put to this string. And what's going on in reality? I'll show you. The magnet actually attract this piece of metal, right? But this piece of metal goes through this flame, and afterward, ideally, it should stick with this magnet, the piece of metal, and the magnet should hold it. But because the flame actually increasing the temperature of this magnet, of this environment, it goes back. And if we build a theory, what's going on, it actually it's getting clear. So what's the idea here? The magnetic materials, we have structure called domains, and this domain contains electrons, and these electrons they have so-called magnetic moment, and this magnetic moment allows them align up or down. The magnetic moment of spin is just some number, can be +1 or -1, and it shows the direction of these electrons in this metal, and sometimes they align with magnetic field, some align up or align down. And when there is some kind, or they can be disordered. So ordered system, everything looking up or looking down, and disordered system, well, we're doing what we want. And here, this process, if we have external magnetic field like a magnet, it attracts because this we have a different poles, right? Magnetic poles. And the magnet attracts these guys, these little electrons, these spins, and when it goes through this environment, through this flame, but the temperature here is increasing. And what's going on? Because the temperature is increasing, the structure is destroyed. They were really ordered here, but now in this, when we have a field with higher temperature, they become disordered. And if we disorder it, the orientation now it's smashing, it's getting new one, really random one. And when this magnet no longer attracting these guys here. And again, when this metal piece here, again, the magnet attracting and it goes through this flame, again is disordered system, disordered state, and it goes back. So it's called the Curie temperature. At certain temperature, metals or other, not only metals, any kind of matter can exhibit such phenomena. Then we can go from kind of order to disorder, and from disorder to order. It's called the Curie temperature. And I want to show you just, if mathematically we, to get it better, we can just get a lattice. And here is electrons, and we have a different direction. In ideal model, again, we can align up or down. You have a magnet, you can put it here and get the needed direction, up or down. In reality, of course, we cannot align up or down. Yeah.
Your shirt's very dark. Could you put it in front of the?
Yeah, I'll just give you to play this thing, okay? And you can see idea. Just want to say, mathematically, it's better to describe this like a lattice. The spins are lining up or down. But as I said, it's an ideal theory. It's looking up or down. In real life, it can go in different direction, and it's more complicated model. Yeah, you can just pass it and play the video. So the trick, if we have a model, the same one, let's say we have, anyway, I want to say in physics, it's called the Ising model, or Ising ferromagnet. When we have a ferromagnet state, when it has magnetic feature, and all these spins are lined down, and antiferromagnet when all the spins are lined down. And at some state we have a paramagnet when the system is disordered. So, and at some Curie temperature, we go from order to disorder, as you saw in this experiment, from order to disorder, from ferromagnet to paramagnet, one state to another, tipping point, passing tipping point. And the simple model what they have, if we're talking using mathematical language, statistic language, the so-called Markov random field model, and the application of a huge one, not only ferromagnet. For example, convection, tropical convection can be described by this model. And we have also two sides where convection may happen, and sides where convection cannot happen. So, and the same way to model the system: spin up, spin down, yes for convection, no for convection. Or for meltwater, if you have spin down, negative one, we have ice. If you have spin up, plus one, we have water. But how to model it? It's a really stochastic random process, and we can just find the probability how the spins are lining up or down at this disordered state. And this probability is a function of energy. And this is the energy. In mathematics, we call it the Hamiltonian. For this lattice system, the energy will be defined through two parameters. How external magnetic field, like a magnet, influence on these spins, and how these neighboring spins, what are close to each other, interacting. And this is the interaction principle. And when we can find the so-called magnetization, when we can count the number of spins aligning up and number of spins aligning down in this disordered state, in disordered state. For this one, it doesn't matter because all of them moderate and it's nothing. But magnetization we need for disordered state. So in the idea, and we can use Monte Carlo simulation to compute it, to get some nice picture. And what we got for meltwater, as I said, meltwater plus one, spin up, negative one, minus one, it's ice. And in our model, we have actually also interaction between neighboring ponds through the heat transfer, because heat transferring from one pond to another, and plus influence of some kind of magnetic field. And if you know this energy, we can compute the probability of coverage for probability to find spins aligned up and down. What is this magnetic field? It's not really like magnetic field of our planet or something like that. In reality, it's really hard question. It's some kind of external field. And we just work on this problem over 5 years. Just this, try to understand this simple equation, what the parameters are. So the magnetic field is a pre-melt ice topography, because the topography of ice pack, it's actually a real driver of formation of meltwater. And of course, it's a random, it's like Gaussian, it's a random one. It's very random one. And then if we think in the interaction between these neighboring spins is big enough, this model reducing to a model with a single parameter only. This H, this parameter is a pre-melt topography, the height of these hills, all these holes actually, and that's it. So one physical parameter can describe the system of phase transition happening in meltwater. And I show the presentation, this movie, what's going on here. You can see starting from small ponds, they forming clusters, and finally it looks like this meltwater. And it's important because this theory, it says if we're forming clusters, it will be a metastable state of this system of sea ice, meltwater, sea ice. And stable state ice, unstable state water, meltwater is a metastable state. Not many things in this universe we have metastable states, but fortunately, meltwater is a metastable state. So it's interesting. And while we say modeling all these things, we say, oh, it works, just because we see something similar. It's not, we cannot say like this. So what they did, they run some simulation and we compare real data for fractal dimension and area with simulated data fractal dimension and area. And we found that the onset of complexity beginning at 90 meters squared. Real data show 100 meters squared. Our model show 90 meters. Also, if we generalize this model, it will be new kind of model in statistical physics called feedback as in models. And we're working on the theory of this model right now. And also potentially this model can describe congregation of people with different beliefs, how we're congregating and forming churches, for example. This kind of potential application of that. And also we can parameterize this model using more images, now satellite images, for example, because we said this model defined from this random field what is the ice topography. Using machine learning, we can better recognize ice, snow, ponds, and get better images to run this model. As well as using GAN machine learning approach, we can get fake patterns of meltwater and feed our model and get different scenarios how these patterns forming, developing, because we don't have real data, enough data, especially this processing, this machine learning satellite images processing, it's quite expensive. But doing some synthetic sampling, we can also run this model and see different scenarios. So this is about the meltwater and sea ice. And it was a disordered system, what has a metastable state and passing tipping points. And I show you how to apply statistical physics, a phase transition approach to study sea ice. And by the way, modeling meltwaters, we can employ this model and use it for Earth system models and advance our model. Now things I told about permafrost carbon feedback, and one of the tipping element of permafrost, what potentially bad for this permafrost permafrost carbon climate feedback. So-called Tundra lakes, or better say thermokarst lakes, but we'll use a simple term Tundra lakes, what actually forming in tundra on permafrost. Permafrost is soil ground, frozen ground, but it's melting not really fast, rapidly like sea ice. And these lakes, actually, what's going on? They can grow if permafrost is melting, or even they can shrink due to some hydrology, some hydrological processes. Because if we're close to a river, let's say, water can pass through this lakes, melting lakes to that river, and we'll get a picnic. The same problem here. It's better to recognize the shape, and we've published some papers on the image processing, again using employing machine learning, what is really nice that we have these tools now for image processing. But we didn't find anything unique in terms of geometry of these patterns, because they maybe it's changing really slow and they don't have any transition, kind of transition. But if you look at this problem from the different angle, we can see another situation. This carbon from permafrost can change the state of the atmosphere. And instead of modeling permafrost itself, we can model permafrost, we can model the atmospheric dynamics. And as I said, we have a frozen ground here, microbes eating this frozen ground, and methane go through the lake. These bubbles you can see them in the winter. And Katie Walter from Alaska, actually, she posted many nice video of these methane bubbles on the surface of tundra lakes. And if you have many lakes, all these methane fluxes into the atmosphere and may change the dynamics of the atmosphere. And the idea is to model this thing. And this model in mathematics, we don't use often numerical models, we use analytical models. And one of these models, so-called the Goody model, was introduced 60 years ago, but still interesting. And this model, it's modeling the atmospheric dynamics, and actually it's the result of this modeling. It can be chaotic state of the atmosphere, and as well as pleasant state of the atmosphere, like within ourselves. What do you have here? But this is the simple series of equations. We need to model fluid velocity, the temperature change, including the radiative term, because radiation, it has a really important weight in this kind of modeling. So it's incompressible fluid, and it's okay because in meteorology there are such models. And we actually put in additional equation describing methane concentration in the atmosphere. And what's going on? On the surface, we have a box, we model in a box. Here, the atmosphere dynamics, and on the surface, we have many lakes, and the methane goes up from these lakes. And as I said, we have an extra equation for methane concentration in the atmosphere. It will be convection term and diffusion term, and also decomposition term, because finally methane disappeared in 15 years. And the methane concentration, it will be a function of, let's say, this alpha is a radiative term, the coefficient describing radiative processes in the atmosphere is the function of the gas concentration. And after that, we analyzing this model, putting some initial and boundary condition on the surface, and how to describe these layers on the surface. It's really interesting. We can just put the function mu, what can describe the methane fluxes, and it's a function of the geometry of these patterns on the surface, plus the Arrhenius law, just the energy, how this we actually go through the energy per year. what we know from chemistry, the Arrhenius. But how to describe this geometry of these lakes? That's a good question. These lakes, we can say they have a circular shape, and where we can say if you have a circular lake, it will be again 1, or otherwise no lake, it will be 0, for example, some kind of this spin ideas. Or we can get deeper and model it. It's another work. I wouldn't spend much time to discuss it. But we can model a melting front, what's shaping the geometry of these lakes. And we employ the phase field model, what actually came from the model what described, introduced by famous physicist Landau for, it was for superconductivity. And this analogy is also really interesting because permafrost, when it's melting, it's an active layer when the melting process is happening. And superconductivity, it's also happening in just in some kind of layer of your superconductor. So it's not for the entire volume. And this idea is, it's like a similarity between different processes. Okay, so the thing is how to model the shape of these lakes, and we choose the simple way. And finally, we just analyze this model for stability, for equilibrium states, and we found this nice picture where the surface temperature will be bistable, and if we have in the increase of methane in the atmosphere, we can switch from one unstable state to the stable state. So now we are here, this unstable state, and if we have methane emission, the huge amount of methane from these Tundra lakes, we can go to a new stable state. So passing these tipping points on the temperature indeed will be increased. A so-called rate-induced tipping point, because the system rate-induced tipping point when the system changing faster when it's the time for recovering of the system. So you have a tipping point and the system recovering, but again, as the system is changing and getting to a new level, didn't wait for this recovery. And you can even compute this level of methane, what we need to get a new stable state. And it's a simple formula just containing some parameters describing this gas. And let's see. And we just substitute these numbers, and we found if we increase the current level of methane by 1,000, 10,000 times, we get this new tipping point, and the planet, our toy planet, will be covered by methane core. And finally, I want to show you the example of the bifurcation in this tipping point when some external forcing actually pushing our system, climate system, to a new state. Here, this is simple energy balance model, what describing how the surface temperature changing due to incoming solar radiation and outgoing solar radiation. And this is so-called a bifurcation diagram, show the path of the climate system described by this equation. And this path, you see, it can be different because it can go through bifurcation points. Now we are here, but if we have a change in the solar constant, for example, we can go to now. It's a very simple way to study this model because solar constant now it's the main external parameter what can be changed because this our star is getting older, and indeed the Q, this parameter solar constant will be changed. And then our climate system can go through go to new snowball system, ice-free system. But this equation can be studied in terms, for example, if we have a albedo, and usually albedo is just a number, but if we take a nonlinear function of the area, let's say our planet covered, it's the Daisy world model. our planet covered by black daisies, what absorbing radiation and changing albedo, and white daisies, what actually reflecting sunlight. And this is a biosphere, what can change the state of our climate system. And it's called the higher hypothesis by Lovelock, introduced by him. And actually, what we are doing here, we describing population dynamics of our species, of our daisies, and how they can, this population dynamics switching the albedo of our system. And this is the equation for the temperature, the surface temperature. And if we change in the albedo in some way randomly, this is a random term actually, when the population dynamic changing the how species consuming albedo, and albedo changing the surface temperature of our planet. And this really important mathematical result for fast slow climate system. And it's indicate new bifurcation, new regions in such system. But again, it's something what is new for mathematics. But finally, we can just compute really nice thing. We can compute, we can see how average biomass and average perturbation of albedo can get our system to a new state. And just solving this equation, we have so-called pitchfork bifurcation when we have three stable points here. And when this pitchfork bifurcation, like a fork, actually goes out three different paths for the system. But why the system is changing in this state? Because the biomass, the biosphere can influence on that system. And this is the main idea. This equation actually confirming theoretically the theorems and everything with a higher hypothesis, with biosphere changing the climate system state. And this is some kind of example of computation. So the conclusion is a very simple one. You know, Arctic is melting. The biosphere is a significant factor for climate change in both ways. But mathematics and physics with nonlinear and stochastic models and artificial intelligence now can actually offer a new path to study tipping points in the climate system. And also it can be useful to improve our models. Current climate models are also great and we can still use it, but we can employ some new ideas. Thank you.
So we can now take a few questions if Ivan's happy to stay a bit longer,
Yeah, sure.
considering we had a bit of technical issues. If there are questions in the room, please just raise your hand, and then online, just send them, or if it's still good and anyone has questions, Patrick, just let me know. We can start from here. I would suggest that I will repeat the question in the microphone so that everyone online hears it, and then we can rotate among different rooms. So, yeah, please go.
Okay, yeah. Thanks for the talk. If I understood correctly, looking at the patterns and water in the Arctic sea ice, you're trying to create a model of the system dynamics, which I guess is maybe a more advanced way to then find out what type of bifurcation or what type of tipping point you might cross, and potentially also when that will happen. I think there's another approach, which is to look at critical slowing down. I'm wondering if that's something that you worked on as well, which can't really tell you when the system will tip, but it will. I think this has been used in some other literature, like looking at satellite imagery of forests and things. Maybe also it's been used for ice sheets. I'm not so sure about that, but there are like some statistical indicators that come from this phenomenon of critical slowing down. I was wondering if that's something that you've also looked into.
So the question is whether Ivan has considered critical slowing down in his research.
Yeah, thank you for this question. So the thing is, so we model these meltponds because first we need to model tipping element like sea ice, and in model should show real situation, because global climate models we just using simple equation of heat conductivity to model sea ice pack, and there is nothing on the surface. But now we have meltponds, what is driver of this climate feedback, the sea ice albedo feedback. And the idea it was to show this mechanism and show a simple model to see what is it's. I wouldn't say it's like really dynamics of meltponds. It's showing the evolution, because statistical physics models, these so-called equilibrium models, they wouldn't show any dynamics. They show how the system passing this critical tipping point. And meltpoint, they just clearly understood what is the physics of meltponds as a metastable state. But there is another work what actually we have. They took this equation for the temperature changes in the Arctic, and they got the albedo as a function of meltpond size. And as you saw, this meltpond size is changing randomly, but there are certain positions when it's a when it has a circular shape, as well as it's like more like a network kind of something. And they study this equation in terms of bifurcation or tipping points, and they found the similar things. When they have the onset of melting, it's dynamics now. It's compared to this statistical physics model. And they found that the onset of melting, when the size is close to 100 meters squared, it's also it's taking our system to a metastable state at some certain temperature. Metastable state of dynamical system what we have. So the ice at some certain temperature is stable, and when onset of melting metastable, and when it has some also unstable state when it's close to water. So we studied the system in terms of bifurcation too. When we incorporated meltponds geometry into such simple model. You're asking about that time series analysis and statistics. Yeah, it's a very huge work. We didn't conduct it, but yeah, it's it's happening. And again, it's not really simple thing, because we took this model, a zero-dimensional model, incorporated geometry and got something, but in reality, many other processes. And this just submitted the proposal to the NSF, like saying, yeah, doing similar what you said, but they said you need to take into account many other factors, clouds, winds, and all this climatology. So not only meltdown. So the problem getting very complicated at this point.
So I have two questions from online that I need to read. So the first one is, can fractal dimensions also be used as a measure of biodiversity and therefore used to understand critical thresholds and transitions in ecosystems? And then I'll ask you the other one later because it's not related.
Yeah, yeah, you can use fractal dimension to study patterns in desert, this vegetation patches in desert, and use fractal dimension as a parameter to describe the geometry. And where many works, I know Mary Silber from University of Chicago, they published some work on that topic. And now think how it's useful, because for meltponds, the fractal dimension we see from observation, clearly it has a kind of transition. But for, let's say, Tundra lakes, we didn't find any transition in fractal dimension. And it's almost constant. It's just certain number. It's 1.6, close to 1.6. For deserts, for desert ecosystem, it may be similar way. So the fractal dimension will be useful if we can note real changes in fractal dimension.
The other question is whether you have considered how to represent climate tipping points in climate emulators or simple climate models.
Yeah, they publish a paper on that. They just can send you to the paper maybe. Yeah, it's a statistical mechanics and climate emulation. But maybe we didn't use tipping points there, but we use this idea to use stochastic, low dimensional stochastic models to improve climate emulators. Yeah, so, but we didn't consider tipping points there because tipping points concept is just because it's a global system, dynamical system. It may be better to use in this context rather than modeling of some climate processes using this climate Earth system or global circulation models.
All right. I guess for everyone in the room, we will now have a networking drinks and kind of thing. So if there are more questions, I'm sure Ivan will be happy to get those. Thank you very much, Ivan, for the talk. Thank you all for attending. The next Changing Planets seminar is on the 28th of March with Tammy Meyer, who is going to join us online. But if anyone wants to come here, we have the room booked. Should we talk about how we can leverage psychology to improve our climate? And if you're interested, most of our talk will be upon a book called Saving Us by Catherine Ahoy. So if you want to read that in advance, that would probably be super helpful. Thank you again. And yeah, see you around.
Когда? Сегодня утром потому что
yeah.